Hello and welcome again to my Physics Online video lecture series. In today's video we're going to be talking a little bit about tangential and centripetal motion. This video is a continuation of the previous video which I made in which we discussed kinematics of motion on a circle. And you'll recall from the last time that we attempted to do kinematics using Cartesian coordinates for a circle, and that this was very, very complicated, that the motion was quite complicated for the object. So I don't really have much of a note to write for our little recall part of this one, but recall that the motion on a circle is quite complicated, or apparently quite complicated, when using only Cartesian coordinates, especially for an algebra-based class. Turns out that even that is maybe a little much, that if the motion is actually uniform, or at least if the object is not speeding up and slowing down, then the x and the y will both have oscillatory motion, which is something that we'll explore in a future video. The point of that last one being that rather than using a Cartesian coordinate system, we should consider using a different coordinate system. So in some sense, the thing that we're recalling is the problem that we ran into, and in some sense, the solution to this problem, or the simplification of this complication, is that we should choose a different coordinate system and attempt to make our analysis in that coordinate system. So choose, in this sense, actually polar coordinates. And polar coordinates, we often use an r and a theta, or an s and a theta, something like that. I'm just going to use r comma theta, even if it's not consistent with some of my earlier notations for this, because this is what is the typical notation you'll find in your textbooks. So even if you're not taking a course from me, odds are, if you're using a standard Physics 1, Physics 2 textbook, it'll be in terms of r and theta, or maybe r and phi. Alright, so let's again draw our coordinate system. It's now in terms of r and theta. We can still draw the x and y axis, can still draw our circle, and if I start off with my object, say right here, then I have an r here, and I have a theta here. This could be maybe my theta initial. This was originally x initial comma y initial. And now the object moves to a final location somewhere else. Maybe it's over here finally. And this final location has the same value for r, but there's now a new theta. So we could call this theta final. We could also call the angle that runs between the initial and the final, we could call that delta theta. So from initial to final, that's a delta theta. Now earlier we established, in a previous video, we established that even if this object is moving at a constant speed around this circle, that it still actually has an acceleration. The reason being that at this moment in time, it has a velocity that's more or less in this direction. So we could call this v initial. And at this moment in time, it now has a velocity that's more or less in this direction, v final. In other words, the velocity is always kind of tangential to the circle. And that means that because the direction has changed, there must be an acceleration. And our analysis got very complicated at that point in Cartesian coordinates. But we can simplify things a little bit by kind of changing the rules a little bit here. Instead of doing just r and theta, or x and y, what if we did another form of coordinate system in which we consider two components, two perpendicular components. So, here's maybe a cross section of the circle, and your object is right here. Now we could have an x and a y, so this would be like y and x. We could have an r and a theta. We could also have, and this is the one that we kind of want to use, one component that's here tangential and one component that's here perpendicular to the tangential component. So this component right here is what we will call center or centripetal motion, and this component right here is what we will call tangential motion. Now, the neat thing about doing it this way is the centripetal axis is the axis along which the acceleration that's causing the thing to turn is always oriented. And the tangential axis is the axis along which the thing is actually instantaneously moving is oriented for uniform circular motion. If you don't have uniform circular motion, then you may actually have a velocity and an acceleration that are not along those directions. And in fact, if it speeds up or slows down, then you still don't have an acceleration just along those directions, but you will have a component that is centripetal. So, introducing a new idea, introducing centripetal acceleration. Centripetal acceleration we will represent with an A sub c. So it's an acceleration A with a subscript of c for centripetal. This means it is center seeking. So the object has an acceleration that is pointed towards the center. In other words, A sub c is pointed or directed to the center of the circle. And this center-seeking acceleration is what causes the object to basically remain on the circle. It's the turning of the object. Since A sub c is perpendicular, to V, tangential, and therefore to V, it doesn't cause the object to actually speed up or slow down. And that's neat, because it means that if you want the object to speed up or slow down, you have to introduce a different acceleration term, namely a tangential acceleration term that modifies the tangential velocity. So again, we're assuming that the object is just moving around on a circle of constant radius. So how do you determine the centripetal acceleration? Well, I'm going to state without proof here, this being an algebra-based physics course, the relationship between the centripetal acceleration and the object's speed and its circular radius. Turns out that it is v squared divided by r. So again, I have an object that's moving about a uniform circle such as this. Here's the center of the circle. This right here is radius r. The object is right here. It's moving with instantaneous velocity v. A sub c would be this speed. A sub c is the speed, v squared, divided by r. And the direction of A sub c will always be towards the center of the circle. So I'm going to draw that in here with the black arrow. A sub c is in this direction. Okay, so that lets us figure out what the acceleration is, and that tells us that the faster the object is traveling, the higher the acceleration needs to be, and the bigger the circle that it's on, the smaller the acceleration is going to need to be, assuming that whichever parameter I didn't say bigger or smaller stays constant. So that's kind of the centripetal part of this motion. What about the tangential portion? Well, again, if I take my circle and I do one of these guys, where the position has moved from this location to this location, I can do in terms of x and y, which I showed was going to be very complicated, but I can also choose to do everything in terms of initial and final angle. In other words, I can sweep out some delta theta here instead of having to sweep out an x and sweep out a y. So this delta theta is related to the actual distance traveled. If this is arc length s, then, or delta s, or whatever you want to call it, then s must be r delta theta. And that's just using basic trigonometry. Again, imagine making the delta theta into a 2 pi, in which case you've gone all the way around the circle once. Then the circumference is 2 pi times r is the distance that you've traveled through that circle. If you go through half of a pi, you've gone through half of a circle, means you have half of a circumference, means you have pi times r that you've swept out, or the distance is pi times r. If you go for a quarter, then you've got pi over 2 times r, and etc. So this right here is telling us the distance traveled around the circle in terms of the angle. Okay, so our distance traveled s, or maybe we should call it a delta s, is r delta theta. So that's the distance that's been swept out. Now remember that r is constant. So I should be able to get essentially a speed, and I can do that by finding the rate change of the displacement delta s over delta t. And so that ends up looking like r delta theta over delta t, which we've defined as, or which we could define as omega, represent by omega, which is called angular speed. So omega represents angular speed. Okay, and then in turn, I could also end up figuring out an acceleration, a tangential acceleration, by taking the rate change of the speed. And so that gives me the angular acceleration. To recap these new terms here, I now have that to recap, I have that the angle swept out, this is dividing both sides by that constant r, should look like delta s over r. Or put differently, we might say theta is simply s over r. And that means that my rate change of angle, my omega, should look like v tangential over r, and my angular acceleration alpha is my tangential acceleration divided by r. Okay, so omega is just simply the rate change of the angle, and alpha is just simply the rate change of the angular speed omega. So now I have a complete set of new terms that I can use to describe the motion on the circle. I have on the one hand a centripetal acceleration that describes the fact that the thing is turning, and now I have a set of kinematics terms, basically a position, a velocity, and an acceleration, that I can use to actually describe the position on the circle itself as this object is moving around the circle. The units are in radians for position, radians per second for angular velocity, and radians per second squared for angular acceleration. And the direction is determined by what's called the right-hand rule, counterclockwise positive, clockwise negative. That's all.